Good afternoon. This talk presents a measure-oriented fuzzy model for continuous maximal coverage, joint work by a team from VN Karazin Kharkiv, National University, Sergiy Yakovlev, Yehor Havryliuk, Andrii Hlushko, Volodymyr Donets, and Nikita Abashin. Coverage problems are a classic topic in location theory. The discrete version, the maximal covering location problem, and the set covering problem, asks which facility sites best serve a set of demand points. The continuous version does the same on real geometric shapes, measuring coverage as area. Both share the same weakness. A point is either covered or not, with nothing in between. In real systems, sensor networks, monitoring, service quality doesn't switch off. It fades with distance, orientation, obstacles. A binary model can't represent this. No partial coverage, no measure of how well a point is served, no way to capture gradual degradation. Fuzzy set theory has been applied to coverage before, but usually fuzziness sits in the demand, the cost, or an external threshold. The geometry itself stays crisp. Our approach is different. Fuzziness is an intrinsic property of the covering object itself, inside a continuous, measure-based model. The contribution has 4 parts. First, geometric parameterization. Shape is separated from placement, described by a pose vector and a reference pole. Second, fuzziness as a property of the object. Its zone of influence is graded, strong at the center, weaker at the edge, and moves rigidly with the object. Third, the maximum aggregator combines overlapping objects' coverage and reduces exactly to set union in the crisp limit. Fourth, a single integral functional with its alpha-level decomposition turns the fuzzy field into one number, computable through ordinary geometric union area problems. The model draws on 3 research threads that have stayed separate until now: classical discrete coverage theory, continuous computational geometry, and fuzzy coverage literature, where fuzziness is usually external to the object. No existing work combines a continuous measure, object-level fuzziness, and one integral functional with a clean alpha-level decomposition. That gap is what this model fills. Formally, we have n covering objects, each a compact set with fixed shape and a fixed target region omega with no placement parameters of its own. Each object's pose, position, and rotation is attached to a reference pole. The global placement comes from rotating and translating the local shape. This separation is what lets us attach a fuzzy membership function to each object later without touching the geometry. In the classical model, the covered region S of P is the union of the placed objects, and phi of P is the area of omega served by at least one object. The maximal coverage problem picks the configuration maximizing phi. Full coverage is never required. The limitation: because phi comes from crisp sets, a point deep inside a zone counts the same as one right on its edge. We replace each object's crisp indicator with a membership function mu, mapping every point to a value between 0 and 1. The intensity of coverage. Membership is carried along with the object's pose exactly like its crisp shape, so the fuzzy model adds no new degrees of freedom, only a richer description. As a concrete example, common in sensor coverage literature, a radially symmetric trapezoidal profile. Coverage is full inside a core radius and drops linearly to 0 by an outer radius. This is a convenient simplification. The model itself accepts any profile, including direction-dependent or empirically calibrated ones. When several objects influence one point, we combine them with the maximum operator. The point takes the intensity of its strongest source. This is the canonical fuzzy T-conorm, the fuzzy analog of set union. And when every membership collapses to 0 or 1, it returns exactly the classical union. An alternative is the probabilistic sum, which treats overlapping sources as independent and reinforcing, always at least as large as the maximum. The maximum penalizes redundant overlap. The probabilistic sum rewards it. We use the maximum for its direct geometric meaning and exact reduction to set union. Comparing the two is future work. The aggregated field is summarized in one number, phi of P, the integral of coverage over omega, like a weighted area. In the crisp limit, it matches phi exactly. The same functional plays two roles, an objective in the maximal coverage problem and a feasibility constraint, phi at least tau, in the full coverage problem. For computation, we decompose the integral. Each object's alpha cut is the set of points where its membership is at least alpha. The configuration's alpha level is the union of these cuts, equivalently where the aggregated field is at least alpha. This gives the layer cake identity. Phi equals the integral over alpha of the area of omega intersected with this alpha level, turning a fuzzy functional into a family of ordinary union area problems. We use three strategies to evaluate this. Exact Boolean geometry on the alpha cuts, most accurate, but repeated at every level. Truncated inclusion-exclusion for many objects with limited overlap, and Monte Carlo sampling, which needs no alpha cuts at all and parallelizes easily. Algorithm 1 ties them together. Start from the area at alpha equals 0, step through increasing alpha levels, computing the overlap area at each, accumulate the trapezoidal contribution between levels, and return the total as the estimate of phi of p. The three strategies differ only in how that overlap area is computed. Here's a concrete example. Three covering objects with core and outer radii, placed at 3 points using the trapezoidal profile. On the left, the aggregated coverage field fading smoothly from each center. On the right, 4 nested alpha levels. Since these are disks, each level is simply a union of shrinking disks around the same 3 poles. This table gives the area at 5 alpha levels, computed by a 400 by 400 grid and by Monte Carlo with 200,000 points. The two agree closely. An 11-level quadrature gives phi around 52.9. Direct Monte Carlo gives about 51.5, a 2.6% difference from quadrature coarseness and sampling noise. Crisp coverage at the core radius gives just 24.4. At the outer radius, almost the whole square, 100.5. The fuzzy value sits strictly between, as theory predicts. Even a coarse 10-level quadrature already matches Monte Carlo within a few percent, practical for use inside an optimization loop. The model keeps geometry, local fuzzy representation, the global functional, and optimization cleanly separated. The same phi of pi serves as either an objective or a feasibility constraint, with no change in definition. Any membership profile fits without modification, and replacing area with a weighted integral lets us prioritize zones. The main limitation, shapes and the region are fixed over time. Moving objects are future work. To summarize, we've built a measure-oriented fuzzy model for continuous maximal coverage, where fuzziness belongs to the object itself, the maximum aggregator generalizes set union, and the alpha-level decomposition reduces the functional to classical tool-compatible union area problems, validated to within a few percent against Monte Carlo. Future directions include a full optimization study, a weighted extension for priority zones, the full coverage constraint, alternative aggregators, and a dynamic extension to moving objects. Thank you for your attention.